So for this question, we're going to be looking at Serena boarding a Ferris wheel, and it's really similar to the question we did in the previous video with Joanna jumping a jump rope at the gym. Okay, so these questions require us to take our knowledge of trigonometry and sine and cosine functions and values and apply them so we can graph them as a function as opposed to a specific scenario with a specific value at that point. So what I mean is we're going to have to create some graph as a sinusoid, which is a sine or cosine function, using the information we're given in this question. Okay, and the reason I call it advanced is because it's just different from what we're used to doing. So the more practice we get, the better we're going to get at it. So let's look at this question here. Serena boards a Ferris wheel at the carnival with a diameter of 20 meters. Okay, so the Ferris wheel, right, this is our Ferris wheel here, has a diameter of 20, or we can think about this as a radius of 10 meters. Okay, the boarding station is 2 meters off the ground. So if this is the boarding station here, right, this is going to be 2 meters off the ground. And we'll say this is the ground. And then this is Serena right here. I know it's a great drawing. So she's walking up to the boarding station. This is where the first seat is. Second seat, third seat. There's kind of seats everywhere along this Ferris wheel here. This is the top. This keeps going around. Classic Ferris wheel. So the seats all around. She's boarding 2 meters off the ground. And it takes 24 seconds for her to get to the top. So from the boarding station to the top, this is going to take 24 seconds. The ideal height to take a photo of the carnival scene on the Ferris wheel is 18 meters in the air. Okay, that doesn't seem to hold a ton of significance for an actual equation that we can develop, but let's leave it for right now. So an equation for her height off the ground with respect to time, that's what we're trying to determine, and also determine the times in the first rotation when she should snap a picture for her Instagram. Okay, so that's what this last sentence was talking about. So at 18 meters off the ground, somewhere about there, how long does it take for her to get there? So let's think about this graphically. So if she starts at 2 meters off the ground, she's not going to go below that because the boarding station is 2 meters off the ground. That's the lowest point that the Ferris wheel is going to go because they want people to be able to board it. So if we think about this as a function of time, right? So if this is our time axis, this is our height with respect to time. Okay, so an equation for height off the ground. So when she steps on the Ferris wheel, when time equals 0, we'll call it, she's 2 meters off the ground. So let's just draw that right there. This is 2 meters. And they also said the diameter of the Ferris wheel is 20 meters, and it takes 24 seconds for her to get to the top. So if she starts at 2 meters at the lowest point, and at 24 seconds, she gets to the top. Well, the top must be this 2, the height when Serena boarded, plus the diameter of the Ferris wheel. Because if she's kind of rotating up, the diameter of this rotation will be 20. So we're just going to add 20 to 2, and that's going to be her highest height possible. So this is going to be, I don't know why, let's just draw it here actually. So at 24 seconds, her height's going to be 22 meters off the ground. And then she's kind of going to come back down to the boarding station after 1 period. And remember, a period is just kind of double what half this period is. Because to get to the top, it takes 24 seconds. So to get back down, it must take twice as long. So this is going to be 48 seconds. And we're going to call this time equals 0 at the very start. So if we're looking for some function h of t, right, first we have to determine if it's going to be a cosine, a sine, and if it's positive or negative. So notice that she starts at a minimum height and then goes up. So anytime we start at a minimum when time equals 0, and we choose a negative cosine graph, we're not going to have a phase shift because all negative cosine graphs start at a minimum like Serena is right now at time equals 0, and then they go straight up, kind of approaching the maximum. So if we do that, then there's not going to be a phase shift, so we're just going to say bx. And instead of x, I'm going to put bt plus our d value. So remember, there's an A here, and the reason there's no C is because there's no phase shift if we choose it to be negative cosine. Now, if we chose this to be a positive sine graph, positive sine typically starts here at 0 and then goes up. So there would be a phase shift in that case, but choosing negative cosine, there's no phase shift. Now let's find the D value. The D value is just the maximum height plus the minimum height divided by 2. So this maximum height here is 22. This minimum height here is 2 at the boarding station. So if we add those together, 22 plus 2, and we divide them by 2, this is just going to be 12 because it's 24 over 2. So our D is going to be 12. So plus 12. Okay, we know what D is. Now, let's think about A. If our midline runs across the height being 12, well, to get from 12 to 22, we have to add 10. And to get from 12 to 2, we have to minus 10. So the amplitude, the absolute value of the amplitude is going to be 10. And remember, it's a negative cosine graph, so this is going to be negative 10 cosine bt plus 12. So now the only thing we're looking for is our b value. And let's remember back to the last video, b is equal to 2 pi over the period. Okay, and the period, remember, is the distance from one trough, one kind of minimum, to the next. And we figured this out to be 48 seconds, right? The units don't matter a whole lot. So it's going to be 2 pi over 48. So this is going to be pi over 24 once we simplify this fraction. So pi over 24 is going to be our b value. Okay, so our final function is going to be negative 10 times the cosine of pi over 24t plus 12. Okay, so for any value, any time in seconds t, we can plug this in for t, right? Solve it with our calculator or by hand or whatever, and it's going to spit out the height that Serena is at on the Ferris wheel off the ground at that time. Okay, so we just did part A. I'll label this part A here. And now for part B, it says, find the times in the first rotation when she should snap a picture for her Instagram. Well, remember in this sentence here, it says, the ideal height to take a photo is 18 meters in the air. So that must mean that h of t, our height, equals 18 for part B. So part B, I'm going to put h of t, right? We always want to rewrite the function just so we start from kind of square one. Make sure we didn't make any mistakes. And we're going to put 18 here for h of t because we're trying to find the time t, this is our variable now, where she is 18 meters off the ground in the first cycle. So negative 10 cosine pi over 24 t plus 12. And the first thing we want to do is get rid of this plus 12. Anytime we're solving for the variable that's kind of embedded inside this the sine or cosine, always want to get rid of this thing on the outside. Work from the outside in. So 18 minus 12 is 6. And now we're left with negative 10 cosine pi over 24 t. Okay, working from the outside in, going to divide by negative 10 because see how this cancels now? And if we reduce the left side, it's going to be, well, we can divide both of them by 2, so it's going to be 3 over negative 5, so negative 3 over 5. That's going to be cosine pi over 24t. Okay, well, we still don't know what t is. Well, we can imagine this kind of thing inside the cosine here to be our angle. It's called our argument. So if we take the inverse cosine of the other side, remember if we have the cosine or sine of something and we take the inverse of that, of the other side, we're going to get what's left on the inside. So this is going to be pi over 24t. Okay, and now we're going to have to use our calculator for this. So we're going to go the inverse cosine of negative 3 over 5. That's going to be 2.214. So 2.214 is equal to the time times pi over 24. Now, if we just want time, we have to divide by that coefficient in front of the t, pi over 24. Okay, so using a calculator, we're going to take 2.214 and we're going to divide it by pi over 24. And this is going to be 16.9. And this is in seconds. So this is one of our answers, but lots of people, they just stop here. We have to actually look at this function and say, okay, does this make sense? And I'll clean it up a bit here. So I'll get rid of these lines. Let's just look at our original function. So we said at 16.9 seconds, her height's going to be 18. Well, if the top is going to be 22, right here at the maximum, 18 is going to be kind of somewhere along this line. Right? This is where it equals about 18. Okay, and right here, right, we're saying that the time, the t-axis, it's going to be 16.9. And that looks about right. It's over halfway to the 24, right, from 0. But it's a few units under, so it's right here, that makes sense. But remember, in her first rotation, she's 18 meters off the ground when she's going up to the maximum, up to the top. But when she passes it, remember, she also hits 18 meters again. So there's 2 points where she's 18 meters off the ground. And if we know that this is 16.9, remember, sinusoids are symmetric. So the distance from here to here is the same as the distance from here to here. So the difference from 16.9 to 24, the distance there, we just do 24 minus 16.9. So this is 7.1 seconds. That must mean that this is also 7.1 seconds. So if we go straight down, this is 16.9. If we go straight down from here, this is going to be 24.1 plus, or 24 plus 7.1. So it'll be 31.1. So these are the 2 times in which she's 18 meters off the ground. So your answer would be, after 16.9 seconds or 31.1 seconds, Serena should take the photo for her Instagram, or about 17 and 31. Because in the real world, who's counting 31.1 seconds exactly? So that's how you can solve this question. I hope it made a bit of sense. How we can kind of apply our knowledge of trigonometry, sine and cosine graphs and functions to solve kind of real world problems. And again, we can apply this to kind of waves in the ocean, springs, different heights of things, anything that oscillates in kind of a repeating periodic pattern like that. So it's kind of cool. I hope you're interested in it, and I'll see you soon.